Welcome to our comprehensive guide on solving and graphing one-step inequalities. In this video series, we'll explore what inequalities are, how they differ from equations, and how to solve them using basic algebraic operations. Let's start by understanding what inequalities are. Inequalities are mathematical statements that compare two expressions, but instead of showing they are equal, they show how one expression relates to another in terms of size or value. The key difference is that equations have one specific solution, while inequalities typically have a range of solutions. For example, x plus 3 equals 7 has only one solution, x equals 4. But x plus 3 greater than 7 has infinitely many solutions, any number greater than 4. There are four main inequality symbols we use. Greater than, shown with this symbol, means the left side is larger than the right side. Less than means the left side is smaller. Greater than or equal to includes the possibility of being equal, and less than or equal to also includes equality. One-step inequalities are inequalities that can be solved using just one algebraic operation. These might involve addition, subtraction, multiplication, or division. Here are some examples of one-step inequalities. Here's the most important rule to remember about inequalities. When you multiply or divide both sides by a negative number, you must flip the inequality sign. This is what makes inequalities different from equations and is crucial for getting the correct solution. In the upcoming sections of this video, we'll dive deeper into each type of one-step inequality, learn the step-by-step solving process, and discover how to represent our solutions graphically on a number line. Let's begin this mathematical journey together. Before we can solve inequalities, we need to understand the language of inequalities, the symbols that tell us how numbers relate to each other. There are 5 key inequality symbols, and each one has a specific meaning that's crucial for interpreting mathematical statements correctly. The first symbol is the greater than symbol, which looks like this. When we write 7 is greater than 3, we're saying that 7 has a larger value than 3. Think of it like an arrow pointing toward the smaller number. The second symbol combines greater than with equality. This symbol means greater than or equal to. When we write x is greater than or equal to 5, we're saying x can be exactly 5 or any number larger than 5. The line under the symbol indicates that equality is included. The third symbol is less than, which points in the opposite direction. When we write 2 is less than 9, we're saying that 2 has a smaller value than 9. Notice how the symbol opens toward the larger number. This is a helpful way to remember the direction. The fourth symbol is less than or equal to. This means the value can be exactly equal to the number, or any number smaller. When we write y is less than or equal to 10, y could be 10, or 9, or 5, or any number less than 10. The fifth and final symbol is not equal to. This symbol tells us that two values are different. They cannot be the same. When we write a is not equal to 0, we're saying a can be any number except 0. It's important to understand the difference between strict and inclusive inequalities. Strict inequalities use the greater than and less than symbols without the line underneath. These do not include the boundary value itself. Inclusive inequalities have the line underneath, which means they include the boundary value. The line represents equality, so these symbols mean greater than or equal to, and less than or equal to. Here are some key examples that illustrate the difference. When x is greater than 5, x could be 6, 7, or 8, but it cannot be exactly 5. However, when x is greater than or equal to 5, then x can be exactly 5, or any number larger. Similarly, when y is less than 3, y could be 2, 1, or 0, but not exactly 3. When y is less than or equal to 3, then y can be exactly 3 or any number smaller. Understanding this distinction is crucial for correctly interpreting and solving inequalities. These 5 inequality symbols form the foundation of inequality mathematics. Mastering their meanings and knowing when to use each one will make solving inequalities much easier. In our next section, we'll learn about a crucial rule that applies when working with inequalities. The rule about flipping the inequality sign. Now we come to the most important rule in solving inequalities, what I call the golden rule. When you multiply or divide both sides of an inequality by a negative number, you must reverse the direction of the inequality sign. But why does this rule exist? Let me show you the mathematical reasoning behind it using a simple example that will make this concept crystal clear. We start with a simple true statement. 5 is greater than 3. Everyone agrees this is correct. Now, what happens if we multiply both sides by positive 2? We get 10 is greater than 6, which is still true. The inequality direction stays the same. But watch what happens when we multiply our original statement by negative 2. If we don't flip the sign, we get negative 10 is greater than negative 6. But this is false. Negative 10 is actually less than negative 6. To maintain the truth of our inequality, we must flip the sign when multiplying by negative 2. Now we get negative 10 is less than negative 6, which is correct. Now, let's see this golden rule in action with algebraic inequalities. I'll show you 3 examples that demonstrate exactly when and how to apply this rule. We have negative 2x is less than 6. To solve this, we need to divide both sides by negative 2 to isolate x. Since we're dividing by a negative number, we must flip the inequality sign from less than to greater than. Let's try a slightly more complex example where we need to be extra careful about when to apply the rule. We have negative 3x plus 5 is greater than or equal to 14. First, we subtract 5 from both sides. Now we have negative 3x is greater than or equal to 9. To isolate x, we divide both sides by negative 3. Since we're dividing by a negative number, we must flip the inequality sign. Finally, let me show you a common mistake that students make and how to avoid it. We have x divided by negative 4 is greater than 2. The mistake students often make is forgetting to flip the sign when multiplying by negative 4. The correct way is to remember that multiplying both sides by negative 4 requires flipping the inequality sign from greater than to less than. Remember the golden rule. Whenever you multiply or divide both sides of an inequality by a negative number, you must flip the inequality sign. This maintains the mathematical truth of your statement. Practice this rule, and it will become second nature. Now we'll explore how to solve one-step inequalities using addition and subtraction. The fundamental principle is beautifully simple. When we add or subtract the same number from both sides of an inequality, the direction of the inequality symbol stays exactly the same. Think of an inequality like a balance scale. When we have x minus 5 is less than 10, we can visualize this as a scale where one side is lighter than the other. To solve this inequality, we need to isolate x. We can add 5 to both sides, just like adding the same weight to both sides of a scale. This keeps the balance relationship intact. After adding 5 to both sides, x minus 5 plus 5 simplifies to just x, and 10 plus 5 equals 15. The inequality direction remains the same, giving us x is less than 15. Let's work through our first example step by step. We need to solve x minus 5 is less than 10. To isolate x, we need to eliminate the negative 5. We do this by adding 5 to both sides of the inequality. Now we simplify both sides. On the left, negative 5 plus 5 equals 0, leaving us with just x. On the right, 10 plus 5 equals 15. For our second example, we'll solve y plus 8 is greater than or equal to negative 3. This involves working with negative numbers. To isolate y, we need to eliminate the positive 8. We subtract 8 from both sides of the inequality. Simplifying both sides, y plus 8 minus 8 equals y, and negative 3 minus 8 equals negative 11. Notice that the inequality symbol direction stays the same. For our final example, let's solve a real-world problem. Sarah has $25 and wants to buy a book that costs $18. How much money will she have left? We can write this as money left equals 25 minus 18, and she wants at least $5 remaining. Let's solve this step by step. We need to simplify the left side. 25 minus 18 equals 7. Since 7 is indeed greater than or equal to 5, this inequality is true. Sarah will have $7 left, which is more than the $5 she wanted to keep. Remember the key principle. When solving inequalities with addition and subtraction, the inequality direction never changes. This makes these types of problems straightforward to solve using the same techniques you already know from solving equations. Now we move to multiplication and division with inequalities. These operations follow similar rules to addition and subtraction, but with one crucial difference that we must always remember. First, when we multiply or divide both sides of an inequality by a positive number, the inequality sign remains unchanged. This works exactly like equations. For example, if we have 3x less than 12, we divide both sides by positive 3. The less than sign stays the same, giving us x less than 4. Notice how the less than sign remains unchanged throughout the process. However, when we multiply or divide both sides by a negative number, we must flip the inequality sign. This is the most important rule to remember. For example, negative 2x greater than or equal to 8. When we divide both sides by negative 2, we must flip the greater than or equal sign to less than or equal, giving us x less than or equal to negative 4. See how the greater than or equal sign flips to become less than or equal. This flip is essential when working with negative numbers. To understand why the sign flips, think about what happens when we multiply by negative 1. Multiplying by negative 1 reverses the order of numbers on the number line. Consider that 2 is greater than negative 1. On our number line, 2 is clearly to the right of negative 1. When we multiply both sides by negative 1, we get negative 2 and positive 1. Now negative 2 is less than 1. The relationship has reversed, which is why we flip the inequality sign. Let's work through our first example. Solve 4y greater than or equal to 20. To isolate y, we need to divide both sides by 4. Since 4 is positive, the inequality sign will not change. We divide both sides by 4. The greater than or equal sign stays the same. This simplifies to y greater than or equal to 5. Notice the inequality sign remained unchanged because we divided by a positive number. Now for our second example. Solve negative 3x less than 15. To isolate x, we divide both sides by negative 3. Since we're dividing by a negative number, we must flip the inequality sign. We divide both sides by negative 3 and flip the less than sign to greater than. This gives us x greater than negative 5. The key step was remembering to flip the inequality sign when dividing by the negative number. For our final example, solve x divided by negative 4 is less than or equal to 3. To isolate x, we multiply both sides by negative 4. Since we're multiplying by a negative number, we must flip the inequality sign. We multiply both sides by negative 4 and flip the less than or equal sign to greater than or equal. This simplifies to x greater than or equal to negative 12. Once again, the crucial step was flipping the inequality sign when multiplying by the negative number. Let's summarize the key points. When multiplying or dividing by positive numbers, the inequality sign stays the same. When multiplying or dividing by negative numbers, always flip the inequality sign. And remember to check your work by substituting values back into the original inequality. Now that we understand how to solve one-step inequalities, we need to learn how to represent our solutions visually. Graphing inequalities on a number line gives us a clear picture of all the values that satisfy our inequality. A number line is our primary tool for graphing inequalities. It shows all real numbers in order, and we can mark specific points and regions on it to represent our solutions. There are two types of circles we use when graphing inequalities. The type of circle tells us whether the endpoint value is part of our solution or not. An open circle, like this one at x equals 2, means that 2 is not included in our solution. A closed circle, like this one at x equals negative 1, means that negative 1 is included in our solution. After placing our circle, we draw an arrow to show all the values that satisfy our inequality. The direction of the arrow depends on whether we have a greater than or less than inequality. A left arrow shows all values less than our endpoint, while a right arrow shows all values greater than our endpoint. These arrows extend infinitely in their direction. Let's work through our first example. We want to graph x is greater than 3. Since this is a strict inequality, we use an open circle at 3. Step 1. We place an open circle at x equals 3 because 3 itself is not included in our solution set. Step 2. Since x is greater than 3, we draw an arrow pointing to the right to show all values greater than 3 are solutions. Now let's graph x is less than or equal to negative 1. Notice this inequality includes the equal sign, so we'll use a closed circle. Step 1. We place a closed circle at x equals -1 because -1 is included in our solution set due to the equal sign. Step 2. Since x is less than or equal to -1, we draw an arrow pointing to the left to show all values less than -1 are also solutions. For our final example, let's graph x is greater than or equal to 0. This represents all non-negative numbers. Step 1. We place a closed circle at x equals 0 because 0 is included in our solution set. Step 2. Since x is greater than or equal to 0, we draw an arrow pointing to the right to show all positive numbers are solutions. Let's review the key points for graphing inequalities on a number line. Remember these essential rules for creating accurate graphs of your inequality solutions. Mastering the visual representation of inequalities will help you better understand solution sets and communicate your mathematical findings clearly. In our next section, we'll apply these graphing skills to solve complete inequality problems. Now we'll work through a complete example to see how to solve and graph a one-step inequality. Our problem is to solve and graph y plus 3 is less than or equal to 5. Step 1. Identify what operation we need. We have y plus 3 and we want to isolate y. To remove the plus 3, we use the inverse operation and subtract 3 from both sides of the inequality. Step 2. Perform the operation. We subtract 3 from both sides. This gives us y plus 3 minus 3 is less than or equal to 5 minus 3. Step 3. Simplify both sides. On the left side, plus 3 minus 3 equals 0, leaving us with just y. On the right side, 5 minus 3 equals 2. Now that we have our solution, y is less than or equal to 2, we need to graph this on a number line. To graph y less than or equal to 2, we start by drawing a number line and marking the key value, which is 2. Since our inequality is y less than or equal to 2, we place a closed circle at 2. The closed circle indicates that 2 is included in our solution set because of the equal to part. Finally, we draw an arrow extending to the left from 2, showing that all values less than 2 are also part of our solution. This represents all numbers that make y less than or equal to 2 true. We can verify our solution by testing values. For example, y equals 1 should work. 1 plus 3 equals 4, and 4 is indeed less than or equal to 5. Also, y equals 2 should work. 2 plus 3 equals 5, and 5 equals 5. Now that we know how to solve one-step inequalities, we need to understand how to properly express our solutions. There are 3 standard ways to write the solution to an inequality: using inequality notation, graphing on a number line, and using interval notation. These 3 methods are equivalent ways of expressing the same solution. Each method has its own advantages and is useful in different mathematical contexts. Let's start with a simple example. Suppose we have the solution x is less than 17. We'll show how to express this in all 3 ways. First, inequality notation. This is the most straightforward way. We simply write x is less than 17. This tells us that x can be any number smaller than 17, but not 17 itself. Second, we can graph this on a number line. We place an open circle at 17 to show that 17 is not included in the solution. Then draw an arrow pointing left to show all values less than 17 are solutions. Third, interval notation. We write this as -infinity, 17 in parentheses. The parentheses around 17 indicates that 17 is not included, just like the open circle on the graph. -infinity always uses a parenthesis because infinity is not a real number. Now let's look at an example with greater than or equal to. Suppose our solution is x is greater than or equal to -3. The inequality notation is straightforward. X is greater than or equal to -3. The equal sign means that -3 is included in our solution set. On the number line, we use a closed or filled circle at -3 to show that -3 is included in the solution. The arrow points right to show all values greater than -3 are also solutions. In interval notation, we write this as -3, positive infinity. Notice the square bracket around -3, which indicates that -3 is included, just like the filled circle on the graph. Positive infinity always uses a parenthesis. Here's a quick summary of the key differences. For strict inequalities like less than or greater than, we use open circles on graphs and parentheses in interval notation. For inequalities that include equal to, we use closed circles and square brackets. Always verify your solution by picking a test value from your solution set and substituting it back into the original inequality. For example, if we solved x minus 5 is less than 12 and got x is less than 17, we can test x equals 10. Substituting 10 for x gives us 10 minus 5 is less than 12, which simplifies to 5 is less than 12. This is true, so our solution is correct. Congratulations! You now understand how to solve one-step inequalities and express their solutions in 3 different ways. Remember these key points. Use inverse operations to solve, flip the inequality sign when multiplying or dividing by negative numbers, express solutions using inequality notation, graphs, or interval notation, and always verify your answers. Thanks for watching. If this video helped you understand one-step inequalities, please give it a thumbs up and subscribe for more math tutorials. Leave any questions you have in the comments below, and I'll be happy to help. Keep practicing, and you'll master these concepts in no time.